Hello and welcome back. In this episode of building a convolutional neural network from scratch in Java, we will be building our fully connected layer. Our first layer, it's like the laying down the nice thick slice of bread in your sandwich. So let's get into it. So creating a new layer, we'll call this fully connected layer. Putting it in our layers package, and this is going to extend our abstract layer class that we made in the last episode. Extends layer. It's going to say, hey, you haven't implemented the things you need to implement. Well, do it. Wow, that's a lot of stuff, but we will get through it. So our fully connected layer, basically we have in this example an input vector of length 4 and an output vector of length 3. For each of these inputs we multiply it by a weight, and the output is the sum of all of the inputs multiplied by their particular weights. So there's a different weight for each corresponding input and output. And we can represent these weights in a two-dimensional array with the same number of rows as inputs and the same number of columns as outputs. And here we can see in this particular example, multiplying x1 by weight 1, 1, x2 by 2, 1, x3 by 3, 1, x4 by 4, 1, and that's for z1. For z2, x1 by 1, 2, x2 by 2, 2, and so on. So that's kind of the general idea of our forward pass. Now, with convolutional neural networks, you can kind of improve this process by helping your network focus on inputs that actually are important. And this is done through an activation function, and the function that I'm going to be using is the ReLU function. So what this function does, it says if this z is less than 0, we're just going to set it to 0, and otherwise it's going to be itself, so we're just going to not touch it. And the reason this is useful is so that we're not kind of punishing and tweaking our network for having negative reactions to certain inputs that aren't relevant. So it just kind of helps focus our feedback on what is relevant. If our network is saying, hey, this is definitely not a 7, we don't want to tweak the parts of the network that are giving us that result that's saying, hey, this really doesn't match a 7, because those parts of the network might be detecting the number 3. So we don't want to cross wires there. So this function basically just sets any negative z value to 0 and any positive z value to z. And then these become our outputs. So our z's go into this activation function ReLU, and out comes our output. Awesome. So let's go ahead and code that. So as we saw on that diagram, what we are wanting is a set of weights. And we also want to track our input length and our output length. Cool, so let's go ahead and create our constructor. And we just want our input and out length, and we will set weights after these. Okay, so we've got our input and our output. Our weight's going to be a new double, which are the lengths of our in lengths and out lengths. So the same number of rows as the length of our input vector and the same number of columns as the length of our output vector. Now, the thing is we want these weights to have some values, so some random values. So we're going to use a random seed. And we're going to use the seed to generate some random weights. So what we're going to do is we're going to get a new random number generator from our Java default library. And that's going to be a new random, and as input our seed. And then for each of our weights along, we're going to set a random Gaussian number, and each of our weights across as well. So just setting our weights at ij to our random dot next Gaussian. So what's a Gaussian? It's a number that's kind of evenly distributed around 0. So it could be negative, could be positive. Nice Gaussian curve, like this kind of shape. So nothing too extreme. We don't want our weights to be like 1000 off the bat. We want them to all be kind of like nicely randomly distributed. Cool. And then we're going to set, yeah, that's it. That's done for that function. So let's call set random weights after we create our weights. And obviously you could end up using custom weights. Feel free to tinker. Random will get you the result you want eventually though, but you know, you can always play with the seed. The reason I like to have the seed as input is so that if you're testing you can use the same seed every time. Also, if you're testing, you might want to create a function where you don't set random weights, but you actually set the weights once to something predetermined, just to make sure that everything's working fine. For me, I don't need that. Again, I've gone through the testing process, but I highly recommend you make some tests of your own for your neural network. Let's go ahead and do the forward pass. Now, the fully connected layer forward pass is pretty straightforward, which we saw in that little PDF I showed earlier. So we're taking our vector input and we're going to have a vector output. Cool, and then for each input node we are going to add its input multiplied by the weight corresponding with that input to each corresponding output node, if that makes sense. Feel free to check back to the diagram so you can really work out what I'm doing here. So we have added all our weights, and now we got to apply our activation function, our ReLU function. Actually, let's call this Z. That's a better name. We're going to call this Z, because Z is kind of our intermediate step in between multiplying everything by our weights and our output function. And the reason I use Z is basically just because there's this great video on this process by 3Blue1Brown, and if you are struggling with this, go watch their video. And hopefully my kind of language here is similar to theirs so that it's not too confusing for you. But anyway, we want to put this Z through our activation function. So let's go ahead and create our ReLU activation function. And this is going to return a double. And it's going to take in a double. And like I said, if input is less than or equal to 0, return 0, else return input. It is that easy. And you can make a neural network without this activation function, but I just find it does not learn very fast, and you often kind of get dead patches in your network where all of the weights get really funky. So yeah, I recommend a ReLU, an activation function. It doesn't have to be ReLU, there are more out there, but we will be using ReLU. Hang on. Let's move this double out equals new. Out length. I see what I've done. That's fine. Out 0 will equal ReLU of ZJ. Cool. and then return out. Sweet, so that's our forward pass. Just to reiterate, so we are moving through all of our input nodes, multiplying each of those input nodes by an output node, and summing that value to the corresponding output node. And then we are running that result through our activation function down here, and then we're just returning that output. Cool, so that forward pass was really straightforward. Let's implement this in our getOutput function. So we need to implement getOutput, we've got our forward pass, but let's use those actual abstract methods that we're overriding from our layer class. So if we get a matrix input, you can see this is why it's useful to have both of these methods. Our forward pass just takes a vector, just a one-dimensional thing, not this list of matrices. So what we want to do is convert, so we'll go double vector equals, and then here's our vector to matrix. Oh, actually matrix to vector, isn't it? Matrix to vector of our input. And then we're just going to call getOutput on our vector. Cool. And we're going to return that instead. So you can see if we get an input that we don't like, we're just going to switch over to here, convert it, and throw it back over to here. And then in here, our forward pass result. Forward pass our input. And then if our next layer equals null, if it doesn't equal null, we will return next layer dot get output on our output from this layer, so passing it down and down and down, and then passing it back up to whatever layer called this one. Or else we're just going to return our result, because we are the last layer in the chain and there's no one else to pass it to. Cool, so that's our forward pass get output completely sussed. The next trickier step is backpropagation. This can be kind of gnarly, so let's take a look at how that works. Here is our fully connected layer forward pass. Let's take a look at what we want to achieve with our backpropagation. So what we want to do is work out how much each of our weights contributed to the error in our final output, because the goal, remember, is to train this network, so to get those weights really fine-tuned to accurately make good guesses. We want it to learn. So how this is going to work is we're going to tell the machine how wrong it was, and it is going to go ahead and update all of its weights so that it gets a little bit closer to the right answer the next time. So what we'll do, we'll take our weights and we'll add the losses for each weight. So what did that weight contribute to our error or our loss? And then we'll get these updated new weights. So how do we find this matrix here? We'll use the chain rule. So this is where your calculus will come in handy. So we get this DLDO, so how much loss the whole layer had from that output, multiplied by our how much the output depended on our z input. So remember that was the function before ReLU, and then how much z depended on w. So from the previous layer we get this DLDO, so we don't really need to worry about that. And then from our ReLU function, well, let's have a look at this. So our output, remember, here is equal to 0 if z was less than 0, or it's equal to z if z was greater than 0. So if we differentiate with respect to z, the 0 is just still 0, and then this dz, so do differentiated with respect to z, z goes to 1, so our differentiated do dz is just o and 1, depending on our z value, and I'll create that function in a minute, it's super simple. And then what is dz dw, so what is our change in z by our change in weight. Well, let's look at z. So this is our equation for z. It's all of our inputs multiplied by all of their corresponding weights in that output column, in the weight column corresponding to the output vector. So our dz in terms of this weight ij, the specific weight that we're looking at, so remember we're trying to get our loss per weight. Ij here would be 1, 1, ij here 4, 2. So our z function in terms of our ij, let's find ij here. Oh, well, it's just xi. That's really easy, so we just need to keep track of our input, and we need to keep track of our z's, and then we can get all of these terms, dl do from here, do dz from here, and dz dw from here. 3 blue 1 brown does a much better job of explaining this than I do, so go check his video out if you're not getting it from my kind of crap explanation. But anyway, this is the general idea. Let's go back to the code. Cool, so looking back at the code now, let's implement our backpropagation function. So coming into here, what we want is our do dz, which is going to be a double. We want our dz dw for each weight. We want our dl dw, so that's how much loss per weight. And this is the value that we're going to use to update our weight. So let's set all of these to the right values. So for each of our input nodes, and then for each of our output nodes, our d0 is going to be our d0 dz. So remember this was so this was our derivative of our ReLU function, equals, and let's write a function for our derivative ReLU. So here's ReLU. Let's just copy and paste that for now. We're going to take another z as input. If our input is less than 0, return 0, else return 1. So these are really similar. We've just differentiated with respect to the input. So input differentiated with respect to input is 1. Awesome. Derivative ReLU, and what are we inputting into this function? Well, we're inputting whatever our last z was. So we need a way to keep track of z. So let's scroll back up here and create an array to do that. And in our forward pass, we are going to set last z equals z over there. Just a heads up is that actually this function here can get kind of annoying because sometimes the weights don't change by anything at all. So what I like to do is add a leak, and this is kind of a good method of getting rid of dead areas in your code, I guess, in your neural network. So I'm just going to create a private final double leak, and that's going to be 0.01. Alright, so where were we? So we have this leak value, so instead of returning 0 if the input was less than 0, we're just going to return a little amount, like a minimum, like a floor. So let's return our leak. Cool, so that is our output in terms of z. Now what is our z in terms of weights? And as we remember before, it was actually just the input, our last input at this point k. So, like with z, we need to keep track of our last input. So let's create a little vector to do that. What's it, last x, I guess? Let's call that last x. And so when we get this input, we're going to set our last x to equal input. And now when we come down here, we're just going to get our last x at k. And so, with this dl do that we get in here, we can set our dl dw to be equal to our dl do at j. So what was our loss in terms of output at j? Multiplied by, so here we're doing the chain rule, our do dz, multiplied by, did I say that right? Oh, d0 dz, that's not what we want. Getting my zeros and my o's mixed up. Do dz multiplied by our duz dw. So all these bits cancel except for our dl over our dz. We are going to multiply this change, so this is how much loss our weight contributed, by our learning rate. So if our learning rate is 1, it's going to change it completely, so that if we put that input in again, it would be absolutely bang on the money. However, obviously, we don't want to just completely train our network to one example, so we want kind of a gradual learning rate. So let's get a learning rate. So let's set our weights at kj. So we're going to update this weight. Minus equals, because we're taking away this change, our loss for that weight multiplied by our learning rate. So the reason this is negative, think about maybe our network outputted a 5 when it was meant to output a 1. So that has an error of +4. We want to scale it down, so we want to subtract from that output, from that weight. Cool. So now we've updated our weights, but obviously this backpropagation needs to be passed back to the previous layer. So let's take a look at how that happens. For our previous layer, we want to find the loss relative to the input of our current layer. So whatever the input of our current layer was the output of the previous layer. The output of the previous layer becomes the input of the next, and so on. So how much did our input contribute to the loss? AKA, what are we passing back to the previous layer? So again, use the chain rule. We're trying to find this dl by dx. We've covered these two, dl by do and do by dz. But instead of dz by dw, when we were trying to update our weights, we're looking for dz by dx. And just the same as the previous one, if we look back here, we have dz by dw equals x, and similarly, dz by dx equals w. And that is summed for all of our j's. So we see this weight ij for zj. But we actually want to find xi, so we sum across all of our j's. So let's go implement that in code. Alright, so because we're summing over our j's, let's do our dl dx sum. Start a new double dl dx sum equals 0. And then for each of these, we will add plus equals, adding our dl do j multiplied by our do dz multiplied by dz dx. So what was our dz dx? Well, if we remember, it was just equal to the weight at k and j. So let's define it up here, double dz dx. So important to set our dz dx before we update the weights, because we are accessing the value of those weights, then updating them, and then adding to the sum for our previous output. So we're adding to our dl dx sum, and then let's create a dl dx. Cool, so we've just set our value here to be equal to the sum of how our x is contributed to the loss over all of our outputs, so over all of our j's. Alright, so finally with this backpropagation function, we want to propagate our dl dx, so our error for the last layer, back to that last layer. So we're going to go previous layer, dot backpropagation dl dx, and it's that easy. However, we do want to check that there is a previous layer, so if previous layer does not equal null. Because this might be the top layer, we never know. And if it is the top layer, we don't want to call nothing. We don't want that null error. Cool, so now we've got this backpropagation on the vector input, this one-dimensional double. Let's suss our backpropagation on our two-dimensional. So same as here, we're just going to convert to our one-dimensional vector. And then we're going to do backpropagation on the vector instead of our matrix. And there you have it, there's our backpropagation. Now what about these other methods? So get output length. Well, this will actually be the length of the list, so technically this should be 0. Output row should also be 0. Our elements is the size of our output length, if that makes sense. This output length is referring to the number of output elements, how many elements are in our one-dimensional vector array output. But anyway, that's all of that sussed. And a car alarm's going off, so I better end this tutorial here, and I'll see you in the next one.